Okay, so now we get to move past Riemann sums and sigma notation because gross, and we're going to transition to really exclusively using integral notation. So let's talk about the ins and outs of this. So again, in this section, we move beyond finite sums of rectangles and explore what happens in the limit as the terms become infinitely small and the number of rectangles approaches infinity. We're going to look at some geometric functions that may contain negative values or area below the x-axis, as well as positive values or area above the x-axis and 0. So when dealing with negative area, it's pretty intuitive. It happens anytime area is below the x-axis, and then when we find the total area between A and B for some curve, it's really a net area, kind of like a net income, where you take in positives and negatives and just find what they combine to. So it's pretty intuitive. It's what you would hope. I think you'll find it not too difficult. So let's do some notation, explanation, and clarification, and all the Asians I can think of. So Leibniz introduced the notation for the definite integral. He and Newton battled it out along with some other people that actually came way before them. That's a whole nother story. But as far as notation, I feel like he contributed a lot to what we still use in calculus. And mostly his notation for the definite integral is the most loved, I guess you could say. The Greek letters of summation become Roman letters in the limit. So the notation here we would read as the definite integral from a to b of f of x, putting it all in words, with respect to x. So again, the definite integral from a to b of f of x with respect to x is how you read this notation out loud. And even each of these parts have their own vocabulary associated with them. We refer to the stretched out S shape as the actual integral itself. And you'll get better at drawing those, I promise. And then we refer to A as the lower limit of the integral. So basically your starting point. And then B is the upper limit, or until you reach this point. So from A to B. We refer to the function we're integrating as the integrand, which to be fair, don't really say that very often, but if you were curious, that's what this particular part is called. And then the dx is the variable of integration, or with respect to. And altogether, this is called the definite integral. And the reason it's called that mainly has to do with the fact that we have bounds. Okay, so it's definite, it's a finite area we're finding because it's between a starting value and an end value here. So the A and B are the important ways to know that it's a definite integral. We will talk about very soon what an indefinite integral is, and it simply means that we take off these bounds. We have no lower and upper limit anymore. So the definite integral can be used to determine the net area bounded by the x-axis, the function f of x itself, and the vertical lines that occur at the lower bound and the upper bound, or lower limit and upper limit. So you're finding that contained finite area. All right, so let's do our first example. We're no longer drawing rectangles anymore, so you should be pretty excited about that. Instead, we're going to do more of a geometry-based approach to finding the area under the curve, or between the curve and the x-axis, until we learn about antiderivatives later this unit. So what you're going to do here is you're going to look at this function f of x. It's clearly been made into some geometrical shapes you'll be familiar with. And you're going to find the area from this lower bound to this upper bound of each definite integral. So for the first one, they want from 0 to 4. So from 0 to 4 is this semicircle here. Remember, the area of a circle is pi r squared, so semicircle would be pi r squared over 2. And it looks like that the radius is going to be 2. So that would be pi, well, not r, pi 2 squared over 2, which would simply be 2 pi. All right. The second one is asking for the area from 4 to 8. So that's, of course, this trapezoid here. And remember, area of a trapezoid hopefully feels pretty fresh. We have a base of 4 and a base of 1 and a height of 2. So that's going to give us, what, 2, and then we average out the bases and we get, what, 2.5? That's, or you could just do 2's cancel. Either way, we get 5. Don't overcomplicate things, Miss Wright. All right, and then we have from 8 to 12 is this triangle here. So remember, triangles are the base times the height divided by 2. So in this case, the base is 4 and the height is 2. And of course, this is below the x-axis, so it's going to be negative area. And it's simply going to be negative 4. So now if we're finding the total area from 0 to 8, let's see, so from 0 over to 8, we're simply going to add the two areas that contains. So that area will just be 2 pi plus 5 all together. And then if we look at 0 to 12, that's the entire thing. So all three areas, including the ones that are negative, being expressed as such. So that's going to be 2 pi plus 5 minus 4, which we could just simplify to 2 pi plus 1. Beautiful. Okay, so now what we're going to do is we're going to set up the integral for the following. And on your notes, it's already filled in, and I want you to express this particular shaded area as an integral. So obviously we start with the actual integral symbol, and if you're feeling lazy, especially on the apex, it's actually advised. You don't actually have to write the 1/9 x cubed. You could, but if you're going to do things the easy way, you're just going to name the function whatever it was named previously. So I could say I'm integrating the function f of x with respect to x, and then all you really have to do is give me the bounds. So from where it's shaded, it's starting here at a lower bound of -2, and it's stopping at an upper bound of 3. And that's it. That's all you would have to say. So that's the minimum amount of effort required to actually answer this particular question. Okay, on the middle one, I asked you to represent this shaded area here. So the most common way people probably do it is to actually write out the function given. Although I will admit I've gotten worse about doing this. I usually just say f of x. But here it's not really named, it's just y equals, so it's going to be required for us to actually write it out. And then our lower bound in this case would simply be -1, and our upper bound would be 4. You don't have to worry about the fact that in that time it goes above and below. That doesn't have to be separated, nothing weird has to happen. You just simply give me the bounds. The function itself will cover the fact that it goes above and below the x-axis. And then for the final one, you should notice that this area looks a little different than the others, right? The others were all coming in contact with the x-axis, and that's what it seemed to be shaded up in regards to. This one is not even touching the x-axis, which is kind of a sign to you. that it's actually not in terms of x that we've shaded. It is touching the y-axis. And so that's what we're integrating with respect to. So this one's kind of a special case. We're integrating with respect to y instead of x. And this isn't super common in this unit, but where we're headed in our final unit with volume and rotational shapes, it could be based on the x or y axis, so you kind of have to get used to this. So if I want to get this in terms of y or with respect to the y variable, it means I need to solve for the x. And this should kind of make you think back to what we had to do for inverse functions. So I would subtract 1 over, and then that would give me the square root of y minus 1 equals x. And it would really be the plus or minus square root, but since we're on the right side of the graph, we're going to leave it the plus square root. So essentially, we kind of get to like not really concern ourselves over that too much. And now I'm going to come down here and set up my integral, and it's with respect to the square root of y minus 1. And then let's be careful with the other details. So the y value it begins at is 1, and it integrates with respect to y all the way up until a y value of 5. So we would say from 1 to 5, and then this would be with respect, with respect to y instead of with respect to x. So whatever your variable is in your actual integrand has to match with what you're integrating with respect to.